Unit 8 is a trig unit. Now, you've had some past experience with trig stuff, but we're going to go a whole lot further than what you've been previously taught. Now, objective 1 is simply a review of some of the things that you've been taught. So I don't think there's going to be anything brand new in here. I'm going to go by sections. This is going to help you with sections 1 through 4. What are the sine, cosine, and tangent functions of a certain reference angle? Well, the first thing we're going to need to do, I've got two sides of a right triangle. So I'm missing the third side. So the Pythagorean theorem is going to help me. A squared plus b squared equals c squared. And c squared is always the hypotenuse. So let's just set up this equation right here. 6 squared plus, let's just call this b squared equals c squared, which would be the hypotenuse squared. So that's the beginning of the equation. So 36 plus b squared equals 100. Subtract 36 from each side, and you're going to get b squared equals 64. So therefore, b is the square root of 64. Technically, it would be plus and minus, but we're dealing with distances, and so distances are never negative. So we're just going to take the positive 8 answer. So b equals positive 8. So we just figured out that this side is 8. Now, knowing that, we can now complete the three trig functions from reference angle B. The sine function, opposite over hypotenuse. So from reference angle B, the opposite is 8. The hypotenuse of the triangle is 10. So we'd have 8 over 10, and we're going to reduce that down to 4 over 5. We're still at angle B as our reference angle, but this time we're looking for cosine. Cosine is adjacent over hypotenuse. So the side that's adjacent to angle B is the 6. And then the hypotenuse is again 10. So this would be 6 over 10, which is 3 over 5. And then one more time, go back to reference angle B and find the tangent, which is the opposite side over the adjacent side. So that would be 8 over 6. And 8 over 6 reduces down to 4 over 3. The next couple of examples are going to help you with problems 5 through 12. Using your calculator and getting the exact answer to a specific trig function. So on my example problem right here, my reference angle is this 34-degree angle right here, angle A, that is known to be 34 degrees. So from this 34-degree angle, this 15 would be the adjacent side. And the unknown value in the problem, what we're searching for, what we're being asked for to solve for, is x, and that's the hypotenuse of the triangle. So what that tells me is cosine is going to be the trig function that's going to help me solve for x, because from reference 34 right here, cosine would be adjacent over hypotenuse. In fact, that's the equation I'm going to write. The cosine of this 34-degree angle equals the adjacent leg, which is 15, over the hypotenuse, which is x. So the first thing I'm going to do is I'm going to solve for x in its exact form. So I'm going to cross multiply. Cosine 34 times x would simply be x cosine 34 equals 15. So I'm just treating that x as if it's a leading coefficient of cosine 34. Now the next thing I want to do is if I want to solve for x exactly, then that simply means I divide both sides by cosine 34. So x equals 15 over the cosine of 34 degrees. Now that's my exact answer. I have now solved for x. But if I want an approximated answer to 3 decimal places, that's where I get out the calculator and I just simply figure out what is 15 divided by the cosine of 34. So 15 divided by the cosine of 34. I'm going to close my parentheses. I probably don't have to, but I'm going to close my parentheses. So 15 over the cosine of 34 equals 18.09. Now we want to go 3 decimal places. So that's a 3. We have to figure out, does it stay a 3 or does it become a 4? Does it round up to a 4? And the answer is it stays a 3. So 18, so x is approximately equal to 18.093. So there are my two answers. My exact answer for x and my approximated to 3 decimal places answer. For this next problem, I'm going to do something very similar to the one right above it. We're going to figure out our reference angle. This time our reference angle is angle B, and it's unknown. So the reference angle is unknown. We're going to call that reference angle x, and that's what we're solving for. Now, we do know a couple of things about that triangle from this reference angle. The opposite side is 9, and the adjacent side is 14. So we know the opposite and the adjacent. What that does is it sets up tangent as being our trig function that we're going to use. So we're going to say tangent of x equals 9 over 14. Now, if I want to solve for x, this is one of those inverse functions. X is going to equal tan negative 1 of 9 over 14. Now, another way of saying tan negative 1, inverse tangent, is arctan. Some calculators have this button. X equals arctan 9 over 14. Either one of those would be a perfectly fine answer for what is the exact value of x. Now, if it's time to figure out what's the approximated value of x, we're just going to go with this one right here, and all we do is we do second function tan, and see how that sets up on the calculator, tan negative 1, and it opens up a parenthesis of 9 divided by 14, and I'm going to close that parenthesis, and what that's going to tell me is the approximated value of that angle to 3 decimal places. So x would approximately be 32.735 degrees. So these two are the exact answers for x. This is the approximated answer for x. Much of the rest of the worksheet involves the use of our special right triangles. Now, you've learned these before, but it's worth reviewing them again because you're going to use them a lot in the remaining parts of this unit. The first one would be a 30, 60, 90 triangle. If that's 90 and that's 30, then angle B must be 60 degrees. Because remember, all triangles equal 180. So this has to be a 60-degree angle. But let's look at this from the 30-degree standpoint. Now, the 30-degree triangle has a certain pattern of numbers that it uses. The shortest side is A, so I'm going to put A right there. The hypotenuse is 2A, so I'm going to put 2A right there. Now, the longer of the two sides, but not the hypotenuse, because the hypotenuse is the longest of the three sides, but this is leg, this is leg, this is hypotenuse. So A, 2A, the longer of the two legs is A square root 3. So, knowing that relationship always holds true in a 30, 60, 90 triangle, then the side opposite the 30, which is the shortest leg, which happens to be A in this problem, would be, the relationship is A, 2A. So if I know the hypotenuse, which is 2A, and I want to go back to the shortest side, which is A, all I do is divide by 2. So 22 divided by 2 equals 11. So I now know this is 11. Just because of the relationship of 30, 60, 90 triangles. Now, the relationship from the shortest leg to the longest leg is simply A root 3. So that means all I have to do is multiply this known value by square root 3. So this is simply going to be 11 square root 3. And that would be my value of B. Now the other one is a 45, 45, 90 triangle. Here's my 90 degree. Here's 45, which means the other one has to be 45. The missing angle is a 45-degree triangle, which means a triangle that has two equal bases, the 90-degree triangle, 45, 45, that means this is isosceles. So the base angles are equal, so this is equal to that. So the relationship is both of these legs are called A, and the hypotenuse is A root 2. So if this leg is 13, then that means this leg is also 13. And if this is 13 and that's 13, then the hypotenuse is simply whatever the legs are multiplied by root 2. So that would mean this is 13 square root 2. Now this might be the most confusing part of the entire lesson, because I don't think you actually did this in Math 2. We're going to start off with the just standard 30, 60, 90 triangle. Here's the 30 degrees. So the smallest of the three sides is the 1, or the A. The hypotenuse is the 2, or the 2A. And the longer of the two legs is square root 3, or A times square root 3. But what if we wanted to standardize this value, the value of the hypotenuse? What if we wanted to say the hypotenuse is the equivalent of 1 unit measure? So see how down here in this triangle, they turned the 2 into a 1. So really that's what we're doing. What do we have to do to turn this hypotenuse, which right now has a value of 2, into having a value of 1? Well, the answer is divide by 2. Well, if we do that to one of the three sides of the triangle, we have to do it to all of the three sides. So that would simply make this no longer a 1, it would be 1/2. And it would no longer make this square root 3, it would make it square root 3 over 2. Now, having said that, let's move on to the 45-45-90 triangle. In the 45-45-90 triangle, again, we see that in the standard 45-45-90 triangle, the hypotenuse is the equivalent of the square root 2, because the other two sides are the 1s. 1, 1, 1 square root 2, or a square root 2. However, it's the hypotenuse that we want to standardize. We want to turn this hypotenuse into having the value of 1 unit measure. So how do we turn square root 2 into a 1? We divide by square root 2. Well, that means these two things have to be divided by square root 2 also. So this would be 1 over square root 2. And since this is equivalent, it's an isosceles triangle, this would also be 1 over square root 2. Now, you might want to think about rationalizing this because we really don't like square roots on the bottom. So multiply the top and the bottom by square root 2 over square root 2. And what you end up with is 1 square root 2, which is simply square root 2 over square root 2 times square root 2 is 2. So we're going to do the same thing down here, rationalize it, multiplying it by root 2 over root 2, and what we're left with is root 2 over 2. There really isn't a homework problem like this, but I'm just going to do one more example of the type of thing that I just showed you. But we're not going to use a 30-60-90 or a 45-45-90 triangle. We're just going to use a right triangle. We have no idea what these other two angles are, but we know this is a right angle, which means I can use the Pythagorean theorem to figure out what this hypotenuse is. Now, I've already set up the equation 5 squared plus 4 square root 21 equals c squared. A squared plus b squared equals c squared. So let's work this out. 5 squared is obviously 25. Now, 4 square root 21 would be 4 squared, which is 16, times 21, which is 336. Equals c squared. Now, 336 plus 25 is 361. So 361 equals c squared. Now, take the square root of 361 and you get 19. C equals the square root of 361, so c equals 19. I made the numbers so they work really nicely. So what we just found out is the hypotenuse is 19. Now, let's go back to the concept that we left on the last problem. What if I wanted that hypotenuse to not equal 19? What if I wanted it to have a value of 1? What if I were standardizing that value? So what do I have to do to turn this hypotenuse into the number 1? Well, I have to divide by 19. And if I do that, that will turn this into the number 1, but that'll turn this into 5 over 19. And that'll turn this into 4 square root 21 over 19. So that's all we're doing when we're turning this hypotenuse into the value of 1. All we're doing is we're saying what is the length of the hypotenuse, and then we're just dividing it by that number because I want it to be a standardized unit of measure. I want that to equal 1.